Hello everybody, and very much welcome to my taster lecture. I'm going to run it as a taster lecture. I'll explain what a taster lecture is in a minute. I'm going to do it on the Fourier Transform, yeah? So the first thing I'm going to explain is why am I doing the lecture on the Fourier Transform, yeah? And one of the real reasons I'm going to lecture about the Fourier Transform is because we're actually using it for this talk. And the Fourier Transform is something you get at university level. You tend not to get it in school and colleges. You're seeing the slides that I'm going to come up with. That's a complicated picture, which is going down a 100 megabit line. Therefore, it must be coded. And there's a good chance that that's done using the Fourier Transform. My speech is coded as well, and there's a good chance that is a Fourier Transform. But it's not definite that it's a transform. So why am I saying that? Well, this talk, we're definitely using the Fourier Transform because you're listening to it. And the Fourier Transform is something about turning signals into frequencies. And that's how your ear actually works. There's a load of little hairs in the back of your ear and the sound comes in and it eventually stimulates those hairs. And so what you hear is frequency. You don't hear the sound, you hear the frequencies that are inside the sound. And that's what the Fourier Transform gives you. So I'm giving you a taster lecture on the Fourier Transform because the whole talk is enabled by this transform technology. And we're going to cover applications. You can see at the bottom, JPEG, yeah, that uses transforms, speech coding transforms. We're going to have an equation as well because there's a bit of maths. We're going to mention architectures and software. It covers everything, and that's why I'm a professor of electronics and computer science, because I just enjoy the whole lot. Now this stuff, I say it's a taster lecture. Of course, it comes from an undergraduate lecture. I do lecture digital electronics, and I lecture image processing at third year level. And so some of my slides come from my third year lecture course, and they're exactly the same slides I use for my students. I'm going to use different words, of course, but the slides are exactly the same as I give to our students. So what is a taster lecture? Well, the difference is online notes. Yeah, we expect people to download the PowerPoints, the lecture slides before they come. We expect people to prepare. Sometimes we get them to do stuff before the lecture. So what does the Fourier Transform do? You know, this is the main nub of the argument. Yeah, how does this thing go? If you look on the left, I've got a signal. Now that might be a signal coming out of a microphone. And or in the microphone into my computer, and then it's being digitized into the computer. And the Fourier Transform turns that into the frequency components of that signal. Now, if you look at that signal on the left, at the top left, you can't see the frequency components there. But if you go down to the bottom, these four things here, and you can see here's a low frequency, and that matches the signal itself quite a bit. There's a higher frequency signal, it doesn't seem to match it at all. There's an even higher frequency signal, and that seems to match it a bit. And there's a very high frequency signal, that matches it a bit. I take these signals and I add them up. That gives me this signal here, the signal that we're going to take the Fourier Transform of. Then I apply the Fourier Transform equation, and that gives me the frequency components here. And I've got four frequency components, so there's four here. There's actually negative frequency because there's a bit of maths, and sorry about that. You just ignore the negative bit. Just take the positive bits. There's four numbers. Those four numbers correspond to these sine waves here. I add up these sine waves and I get that signal. Now over here, there's only four numbers. Over here, there's a lot more because there's different numbers. As we walk down this signal, you get different numbers, yeah? So to code this signal, it's going to take quite a lot of information. This one's much easier because it's only four numbers. So that's what the Fourier Transform does. It allows you the coding, and you can compress the signal. And that's the basis of video coding. It's the basis of speech coding as well, or one of the bases. It's not the absolute basis, yeah. The Fourier Transform gives you separation in frequency of a signal that has been added up in time. And that is the main purpose of the Fourier Transform, is separation in frequency. There is an inverse Fourier Transform. We can go the other way and you can see there's, that's shown on the picture. We can go one way, the Fourier transform, go back, reconstruct the signal. So we can play over here and then go back to where we started from. Now, we're going to go to a picture now. Whoa, blimey, why is he mentioning this picture? Yeah, well, this is a Salvador Dali picture. And it's a picture of his wife looking at the sea, but it's a very high frequency picture. If we look at the low frequency pictures, we see a different thing. Dali was a clever guy. Yeah, look at that. Now, can anybody, using the chat button, can anybody say who's in that picture? Now that I've changed the resolution, I've gone from high resolution to low resolution. Can anybody see somebody's face in that picture? I'm looking at the chat line here. Oh, well done, Lincoln. Yes, you got it. And Dali knew it. He's, Dali's a clever guy. If you look down at the bottom here, here's a picture of Abraham Lincoln on the bottom. Dali was so clever. He knew that if you took this picture and turned it into a low resolution picture, you got something that looked like Lincoln. Now that's dead clever, yeah. And that's what frequencies are about. And these are frequencies inside a picture. So these are waves, and this is waves inside a picture, a bit like the waves in a sea, yeah? Things that go up and down in 2 dimensions. So waves aren't just in speech, in a microphone. You get sine waves and cosine waves in pictures as well. And you can see it here with the cloth, yeah? Here you can see there's sine waves and cosine waves. And as I go across, I get change. And that's why this axis underneath, this is the transform underneath, and it's an axis, it's along one axis, because that's where the change is. If I walk down the cloth, I don't get much change. And so there's no vertical frequencies. I only get horizontal frequencies. When I go over to the picture of the tablecloth, I've got frequencies up and down. And that's why I've got these blocks here in the transform. But if you look at those transforms, most of the transform is empty. There's no numbers there. So that's why we can do coding based on these transforms, because we just need to look at these numbers in the middle, and that will represent the picture. And so we do have coding via the Fourier transform, and that's why this taster tool is probably using the Fourier transform in your ears. So Fourier was the first guy to say this. He was a clever guy. He was a French guy. I've got his book here. I've got props. 1878, this copy. It was the first English translation. And he said, he was the first guy to say that you can make up signals by adding up sine waves and cosine waves of different frequencies. Now, when he did this in 1807, it was radical. It was so radical that people were skeptical. Lagrange and Laplace, famous mathematicians, they rejected his work. They didn't like it. They said, no, you can't do this. It won't go to infinity. Yeah? He persevered. He had the tenacity to persevere. And yeah, the book came out in French. This is an English translation. And look underneath. I've got a quote here from James Clerk Maxwell, which is, I've actually taken out of the back bit of the book. Fourier's Stress, this is one of the very few scientific books that can never be rendered antiquated by the progress of science. And that's by James Clerk Maxwell, a really famous guy, yeah? Now, the whole of this thing, we can split the speech wave into its component sine waves and cosine waves. So there's a bit of maths. This is the equation I'm going to go to. This is a sort of picture of Fourier on the right. Essentially, let's do it in a simple way. U is frequency, T is time. We calculate something in terms of frequency, f, p of u, as a function of time, a function of p of t. So we get frequency from time. That's what Fourier is. It decomposes stuff into frequency. Now, how do we do it? Well, it's we actually use integrals, yeah? And it's a summation, that's the S in integral. It's an integral from minus infinity to infinity with respect to time, and that gives us frequency. And then we stick in a little bit in here. Whoa, this is the nasty stuff, because there's a minus j 2 pi ut. Now that j, that's the complex number, e to the minus jt. This is Euler's formula, cos 2 pi ut minus j sine that. For those of you who've never seen complex numbers before, J is the square root of -1. You'll say, oh, that can't exist. It's the square root of -1. Well, it must exist because J squared is -1. For those of you who've seen it before, yeah, those complex numbers, when I did them at school, they seemed to be completely useless, yeah? But we use them all the time. They're really good, yeah? Because these complex numbers give us magnitude and phase. And the phase is the tan to the -1 y over x. The magnitude is the root x squared plus y squared. The magnitude is how big something is, and the phase is when did it happen. And complex numbers allow us that. That's brilliant, yeah. We can't do it with normal math. So we use those complex numbers all the time. For some of you who are perhaps a bit, whoa, I haven't seen this before, just consider it an operator at the moment. Yes, there is that J, and it's complex numbers, yeah. And but it is really important, and we do use them a lot. At university level, we consider complex time. We don't just have real time, we have complex time. When did time happen, yeah? And it's a notional abstraction that we have to have. Now, of course, in that, it's maths. You might be frightened a bit of maths. Now, in electronics, we expect people to do quite a bit of maths, yeah? So never to be frightened of maths, yeah? In computer science, people don't do as much maths, yeah? We don't require absolute maths in computer science, but we do more in electronics. How do we implement the Fourier transform, that equation? Yeah, well, of course, we actually implement it using software. And it's called the fast Fourier transform. It's an algorithm which implements it at high speed. Here's a version of it I wrote, and it's not actually very long. I've left out a couple of lines here where I'm just copying stuff across. The bit that took me donkeys to work out was these pointers in the middle. Yeah, getting those pointers right, that took me ages. Yeah. The architecture is that you combine two 2-point FFTs to give you a 4-point, two 4-points to give you an 8-point. It works on 2 to the n samples at a time. So, and this software is actually just employing this architecture here. So yeah, there is hardware. You can buy Fourier transform chips or implement it in FPGAs, or you can write software as I did. This software, by the way, is written in a language MATLAB, which is a very simple language. Yeah. It's really just for teaching. So what other support material do I expect my students to get? Well, they will get worksheets, MATLAB, MathCAD, any programming language that I can use. They'll get online software, and they read one of my shelf of books as well. This is Feature Extraction and Image Processing for Computer Vision from the library. And that describes the Fourier transform in a lot more detail. What does the Fourier transform do? It also allows us to do filtering, yeah? And I can do low pass filtering. I can select the low frequencies there. That's like coding, really. You can still see the lady's face, but the amount of information is very small. The next bit is the most important features in the face, and that's the high pass filtered transform. And Fourier allows us to select these different components and present pictures in different ways. It's fantastically useful. Now, we use it in our research as well. So I'm going to go to, I'm going to just have a me on television time, and I'll explain why the Fourier transform comes into this. And it's about my research. And we invented the systems that recognize you by the way you walk. So I'm going to play you that video now.
A new tool police have at their disposal. The simple act of walking. Researchers in Britain can now identify criminals based solely on the way they walk. It's been a decade in the making and soon may be used right here in the US. And ABC's David Mirror joins us here with more.
Diana, Bill, this is really something. Investigators have long had fingerprints, DNA, and facial recognition. Apparently now they have this, a simple walk. And what they tell me is the way I just walked from here to there is unlike anyone else out there. From John Wayne's superstar swagger in Rio Grande to Giselle's supermodel sachet, they are walks you can identify a mile away. But scientists say what we see on the catwalk can be applied to the perp walk, convinced the way a criminal walks can give them away.
Everybody appears to be unique by the way they walk.
Professor Mark Nixon says he has the evidence to prove it. The British researcher and his team have developed what's called automatic gait recognition, a 3D computer program that analyzes the way a person walks. It will allow investigators to match images caught on tape to a suspect's walk.
Taking a sequence of frames from a video camera, putting them into a computer, and then deriving a set of numbers for people who are walking in those video frames. And the set of numbers is unique for a different person.
No one else is walking like you on the planet. Unless you have a twin brother somewhere.
New York sports trainer Pat Panacchia has also launched a study on gait, hoping to prove it's as unique as a fingerprint. There's a lot that goes into it: muscle strength, bone length, and body mass.
So if you studied my gait, my walk, you could identify me in a crowd?
Sure, absolutely.
He points to the scene in the movie Usual Suspects, in which Kevin Spacey's character is identified by his walk. In real life, the British team began its work after these chilling images caught on tape in 1993 of a toddler being led away from a store. That toddler was later killed. And in this country...
Yeah, I'm going to stop you there, and then let's get back to the presentation. Okay, so that's gait recognition, yeah, and that's my research field, yeah. Now, the important thing in that is that your gait, the way you walk, can be represented by a set of numbers. So we have to get hold of that set of numbers. And so how do we get hold of a set of numbers which is unique to you? You've got your own different set of numbers. Well, what we do is we measure the inclination of the leg. You can see this lady's leg. Her legs are swinging, and her thigh and the lower leg. And there's an angle, and that changes with time. That's the waveform. We look at that waveform, and we can't see anything really. And what we do is we take the Fourier Transform, and whoop, we get a set of numbers. It's brilliant stuff. And we get your set of numbers from applying the Fourier Transform to this signal in the middle of the picture here, yeah? And what are those? So what do those frequencies represent? Well, here is how somebody's leg moves, yeah? This is the simple harmonic motion, for those of you who've done that in your courses, yeah? That, of course, isn't somebody walking. That's just a grandfather clock, yeah? We need to make it move. So we add a bit of motion to the simple harmonic motion, and then it moves, and that's a grandfather clock on the back of a lorry. What we need is somebody walking, and that means different sine waves. When we add that together, we get that. Now you'll be saying, whoa, hey, God, how do I know that's the way somebody's walking? Because you've never seen a single human thigh walk in front of you. Now, they tend to be connected to the rest of the body, yeah? And so how did I get that? Well, that's the picture in a different way. And it comes from this guy here. And it's his thigh moving along. And that's the selection of frequencies you see. And the Fourier Transform allows us to get that set of frequencies. And those frequencies are different for different people. And then we can recognize you. The biggest database for recognizing people by the way they walk is now up to 100,000 people. And so that's my friends in Japan. They show that surprisingly, the way you walk is unique in very large population databases. So let's see, you can use your chat box now, and let's see how good you lot are at Gait. Let's see, this is a young man. Is he 414 or 24? Anybody going to have a go? 414 or 24? Somebody on 414, yeah, mostly 4, I see, yeah, mostly 4. Yeah, just the odd 14, nobody's going for 24. Okay, so let's see what he was. Yeah, he's 4 years old. So let's move to the next one. Right, 62, 72 or 82. What do you reckon? 62, 72 or 82? Pop it on your chat box. Yeah, 72, 72. Hang on, I should tell you, this guy is Japanese. They live a long time in Japan. Is that, oh yeah, up comes an 82, very good. Yeah, everybody's changed to 82. And that is, of course, the answer. He's 82 years old. And then take mum. Oh, yeah, is mum 24, 34 or 44? 34, 34, 44, 44, 24. Yeah, she's 34 years old, yeah. Your guesswork on that, you know, you were as good as me, you know. Can you get anybody's age correctly from the way they walk? You get about 60% of them right. And how much would a computer get? Well, we do use our computers to estimate people's age from video, and we get it 95% correct. So there's a lot of information in the way you walk. It's not only the fact we can recognize you, actually we know what your gender is, and we know how old you are as well. So it's an incredibly powerful thing, and that's computer vision, and that's the research I do with my research students. Okay, so and that's of course the Fourier transform, we use that. And for those of you like those complex numbers, yeah, here's the importance of phase. Complex numbers give you phase, yeah. We tend to talk about the magnitude all the time, but the phase is really important. And that Fourier transform, we can reconstruct it from magnitude and phase. So I've got a face and I've got an ear. If I take the magnitude of the ear and the face of the face, that gives me this picture here on the bottom left. That is the face. So the phase gives you the information. That phase is incredibly important. When I take the magnitude of the face and the phase of the ear, I get an ear. It's incredible, yeah? So we tend to, when people lecture on the Fourier transform, you see the Fourier transforms as pictures of magnitude. The one that's more important is actually the phase. And so those complex numbers are dead useful indeed. What are the applications of the Fourier transform, yeah? Well, we use it in science for understanding and analysis. We can analyze the signals, we can understand what makes them up. We can do it optically, we can do it using computers, there's lots of ways to do it. And they decompose the signals, and they split those signals up into the underlying sine waves, cosine waves. That fast Fourier transform is actually one of the most beautiful algorithms in computer science. I think it's brilliant because it makes the Fourier transform usable in hardware and in software. And you can use it to speed up algorithms. It gives you a fantastic advantage in speeding stuff up. There is representation as well. You've seen the cover of Pink Floyd's album where the signal gets split into its component frequencies. There is beam forming. How do they find submarines from arrays of microphones? It's the same sort of thing done in reverse. And the Fourier transform allows you to do it. It's used a lot in coding. There's a lot of transform-based codecs because it gives you access to the frequencies, and that's a very compressed format. WMA, Windows Media Audio, JPEG, Joint Photographic Experts Group, movies, yeah, they all use transform-based coding. JPEG uses wavelets, and WMA uses a DCT. And these are all variants of the Fourier transform. The Fourier transform was essentially the first thing that allowed us to do it. We do use it for seismology. We do use it for face recognition. We use it in my research. You know, you can see this lady over here. You know, that's part of my research in computer vision. Over here, this is the research in gait recognition. I work in biometrics and I use Fourier transforms all the time, and my students use them a great thing. We use them in seismology, we use them in medicine and space. There's a fantastic number of applications of the Fourier transform. What he did in 1807 was he said that signals can be split up into frequencies, and he started off with a set of equations, and we're still working out those equations. We're still using those equations. We're using them now. We use them in our hearing. We use them all the time. And so Fourier is an enormous part of our modern life. You never hear of him, you hear of Kim Kardashian and all that lot. But Fourier is the guy who actually revolutionized our life. So this was just an introduction, a very focused introduction. And I hope you enjoyed it, and it gave you a feeling of what a university lecturer's life, even in these online times,